Hello everybody, getting ready to do lesson 7.1 part 2 of pre-calculus math, systems of equations. And for part 2 of 7.1 you got 20 points here. It goes in your notebook, so have your notebook guides ready or your notebooks open. And then 48 points here will go into your classwork sheet. And today we have a bell work. Hooray, we got a bell work, students, teachers, we got a bell work. So in these exercises, find the domain of the function. What's the domain of this function? And identify any horizontal or vertical asymptotes. So remember that, students. Give your students about 5-6 minutes. Graph these, students, too, by the way. Okay, 5 minutes. Okay, welcome back for today's solutions of today's bell work. F of x equals 5 over x minus 6. So domain is all of x except x cannot equal 6. And then our vertical asymptote will be x equals 6. No zeros down here in your denominator. And then the horizontal asymptote will be y equals 0 because you don't have your degree in your a denominator is greater than your degree in the numerator. And okay, for 2x minus 7 over 3x plus 2. X cannot equal negative 2 over 3. Vertical asymptote will be x equals negative 2 over 3. So we got a vertical asymptote over here. And then our horizontal asymptote would be 2 over 3. So it would be the quotient here of your coefficients of your variables here. They're both the same degree. So you have a horizontal asymptote about here. Graph those, students. Go ahead and graph them. Into our today's lesson. Example 4, substitution, no solution case. So solve the system of equations. Here is our solutions of equations here. Negative x plus y equals 4. That'd be equation 1. And then x squared plus y equals 3. That's equation 2. Begin by solving for y in equation 1. So let's solve for y up here. And you'll get y equals x plus 4. Next, substitute this expression for y into equation 2. We know what y is up here. And solve for x. So here is our equation 2. Then we're going to substitute in for y. X squared plus x plus 4 equals 3. Okay, into our second page here. So we have x squared plus x plus 1 equals 0. This is your simplification after we inserted our value there into our system. And then we come out here, x equals negative 1 plus or minus radical 3I over 2. After we plug in these values into our quadratic formula, this is what you come up with here. And because this yields two complex values, the equation x squared plus x plus 1 equals 0 has no real solution. So the original system of equations has no real solution. Okay, let's try one now. To solve this system by the method of substitution, use a graphing calculator to verify your results. So we got this system here. And then this is yours down here, students. But let's do this one here. So equation 1, equation 2. Solve for y in equation 2. So we get y equals x minus 2 for equation 2. Y equals x minus 2. Substitute for y in equation 1. And we get 2x squared minus x minus 2 equals 1. And then we distribute our negative 1 through our parentheses, and we get 2x squared minus x plus 1. And there would be no real solution for this. Once you plug that in or you try to graph that thing, you'll find no real solution there for that one. And then I don't do that. That's up to you. Okay, so into our classwork. For examples 1, 3, and 4, you can see that a system of two equations and two unknowns can have exactly one solution, more than one solution if it's got like a parabola or something, or no solution. So the two equations in example 1, the graph has two lines with a single point of intersection. This was from example 1. And then the two equations in example 3 graph, the example 3 graph has a parabola and a line with 2 points of intersection. This thing here would have two solutions for this. So example 5 shows the benefit of a graphical approach to solving systems of equations in two variables. Notice what happens when you try only the substitution method in example 5. You obtain the equation x plus natural log x equals 1. It is difficult to solve this equation for x using standard algebraic techniques. In such cases, a graphical approach to solving a system of equations is way more convenient. You can graph and find a solution way faster. Okay, so let's try one like that. Solving a system of equations graphically. Solve this system of equations. Here's equation 1, equation 2. So from the graphs of these equations, it is clear that there is only one point of intersection between these two equations. Use the intersect feature of a graphing calculator to approximate the solution. So here's a graph here. Here's your natural log curve here. And then here's your line here. And then this would be your solution right there. Point as 1, 0. So this is where it intersects your x-axis there as well. So that would be your solution there for example 5. You can confirm this by substituting 1, 0 into both equations. So check 1, 0 in equation 1. So y equals natural log x. So when we substitute in, does 0 equal natural log 1? It does. It does equal that. And then for 1, 0 in equation 2, when we plug that in, x plus y equals 1, it would work. 1 plus 0 equals 1. So the equation does check. The solution, rather, does check for equation 2. Let's try one now on our own. Use a graphing calculator to approximate all points of intersection of the graphs of equations in the system. Round your results to 3 decimal places. Verify your solutions by checking them into the original system. So we have x plus 2y equals 8, y equals 2 plus natural log x. Here's our graphing grid. So what do we have here? We have x plus 2y equals 8, and then y1 would be, for y1, would be 4 minus x over 2 when we solve here for y. And then y2 for c, y equals already, this is already solved for y. So we have two solutions here. We have a y1 and a y2 here. So when we graph these two lines here, this is our line here for 4 minus x over 2. This would be our line here, and then this would be our natural log curve up here. And so right there, you know that would be our solution there for that. Point of intersection would be 2.318 and 2.841. So to find that up here, it'd be a little difficult, but when you use your intersect feature of your graphing calculator, that comes right out real nice. Okay, application. The total cost C of producing X units of a product typically has two components, the initial cost and the cost per unit. When enough units have been sold so that the total revenue R equals total cost C, the sales are said to have reached the break-even point. You will find that the break-even point corresponds to the point of intersection of the cost and the curve. So when we break even, they both cross each other. So break-even analysis, a small business invests $10,000 in equipment to produce a new soft drink. each bottle of the soft drink costs 65 cents to produce and is sold for $1.20. How many bottles must be sold before the business breaks even? Okay, so the total cost of producing X bottles, here's our verbal model. Total equals cost per bottle times number of bottles plus initial cost. So let's fill those values in. The revenue obtained by selling X bottles, here's our cost function. Our revenue function would be price per bottle times number of bottles. Okay, that sounds about right. So revenue equals 1.20x. That's a revenue function. So because the break-even point occurs when R equals C, you have C equals 1.20x. So our cost would have to equal our 1.20x. That would be our break-even point here. This is where it would occur. And the system of equations to solve would be C equals 0.65x plus 10,000, because we got an equipment investment, and then C would equal 1.20x. So we have two cost functions here. Now you can solve by substitution. So C equals 0.65x plus 10,000. Equation 2, well, what are we going to do here? We're going to substitute in 1.20x for C. So, okay, so we already solved that for C in the earlier one. So now we substitute that in. So now we can solve for X. So we need to find the amount that we need to produce. So we move this over here and we get 0.55x equals 10,000. And then we divide through by 0.55. And what do we get? We get 18,182 bottles before we break even. So, okay. That's our break-even point there. And then this would be your graph here. Anything down here would be a loss. Anything up here would be profit. And then here is our revenue and cost. Revenue and cost in dollars. So here would be our number of bottles. This is our output here. And then this is our dollar output up here. So we have a break-even point about there. Would be that. And then we got to produce 18,182. That would be there. So 18,182 come up here. And then your dollar amount would be up here. So anything up here above that would be profit. Now, revenue less than the break-even point corresponds to an overall loss, whereas revenue greater than the break-even point corresponds to a profit. Verify the break-even point using the intersect feature or the zoom and trace features of a graphing calculator, which this is done very nicely. Okay, let's try one. Here is our problem here that will be on your classwork sheet. Okay, so to solve our break-even analysis guided practice problem here, a small software company invests $16,000 to produce a software package that will sell for $55.95. Each unit can be produced for $9.45. Write the cost and revenue functions for X units produced and sold. So here's our total cost. Here will be the sum of the variable costs plus the fixed cost. So we have 9.45x. That'll be our, for each unit, it's 9.45 plus 16,000 here is our fixed cost. And then down here, the total revenue is the selling price times the number of units sold. So it'll be R equals 55.95x for that. And then use a graphing calculator to graph the costs and revenue functions in the same viewing window. This is your independent practice, students. Use the graph to approximate the number of units that must be sold to break even and verify the result algebraically. So do that algebraically as well as graphically. And this is 4 points back here. Do I do this one for you? Do I help you? I do. Here's your revenue line, and then here's your cost line here. So that would be your break even there. is the point of intersection of the cost and the revenue function. So 55.95x equals 9.45x with 16,000. And when you solve for x, you get 3.44 units. So it'd be 3.44 here. At whatever dollar amount that is, I'm not sure what that would be. So when x equals 3.44, it would be 16,000. So this would be your 16,000 here. And that's your 7.1 part 2 of systems of equations. If you need solution PowerPoints or any other materials for this course, email me here. I'll get those out to you. Thank you very much.